Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at Raoult's law. So last time we looked at Henry's law, which looked at essentially the vapor pressure of a solute as I change the concentration, or conversely, how the concentration of the solute can be reflected by its vapor pressure. Today we're going to be taking a similar look by now looking at the solvent. We've already kind of looked at what happens when I'm looking at a solvent vaporizing, as we've looked at the vapor pressure of pure water. However, one of the important things is when we looked at this vapor pressure, we assumed that water was pure. And at which point, turns out our vapor pressure is the same as the equilibrium constant. However, something kind of interesting happens. If I take my pure water and I really start making a solution out of it, I start adding in more and more solute, what I'm going to do is watch the concentration of the solvent slowly decrease. And as a result, there's going to be less, in this case, water to vaporize, which will end up affecting the real vapor pressure. And so what we're going to be looking at is, as I start mixing together a solution, what is going to quantitatively happen to the vapor pressure of my solvent. So if the liquid concentration has significantly changed, it turns out that it will actually show up in the equilibrium expression. But where gases show up as pressures and solutes show up as molarities, it turns out that solvents and liquids and solids show up as mole fractions. So this means that I can now give my equilibrium constant as, again, products over reactants, but now it's going to be pressure of water over mole fraction of water. So this will apply for any sort of liquid gas interchange, where it's going to be the pressure of whatever my gas is over its liquid counterpart. So if I've got a so my equilibrium constant for this reaction will stay fixed, as the Gibbs free energy of this reaction will not change, and it will still be the vapor pressure of the pure liquid, where the pure liquid is represented by this star. Now, if I've got a pure liquid, what ends up happening is that my mole fraction is going to be 1, because all of my substance is the liquid. Now, what we're going to note is that as I start adding in solute, we're going to watch the mole fraction of the solvent decrease, which as a result will change the effective vapor pressure of my solvent. So what we can do is rearrange our previous expressions, replace our equilibrium constant with the vapor pressure of the pure liquid. And by convention, this is typically referred to as Raoult's law, where the vapor pressure of my solvent is given by the mole fraction of my solvent and the vapor pressure of the pure solvent. So again, star represents pure, no star represents the actual system I'm working with. And what we're going to note here is that our pure vapor pressure is only going to depend on 2 things: the identity of the substance and the temperature. Identity of the substance will change the Gibbs free energy of the reaction. And because, as we've seen previously, this reaction is dependent on entropy, it will change with temperature as well. So this ends up giving us a way to calculate the vapor pressure, again, with a changing concentration of a mixture. And again, we're going to see the observed vapor pressure is only going to depend upon essentially the identity temperature, so that pure vapor pressure, and the total amount of solute added. So because as I add more solute, I'm going to decrease the mole fraction of the solvent. So anytime we have a property that only really depends upon identity and the concentration of a solute, this is called a colligative property. It doesn't depend upon what solute I add, just how much of it. So what we're seeing is that as I end up adding more solute, my solvent will decrease in concentration, the mole fraction will go down, and what ends up happening is it becomes more entropically favored for the solvent to stay in the liquid phase, because remember, the entire reason the solvent is evaporating is because it's entropically favored. As I make my solution more disordered, there's less to gain by evaporating. So what ends up happening is we're going to see a decrease of concentration of the in the vapor phase, again represented by vapor pressure. Now, it turns out you can extend this idea as the concentration decreases to such an extent that A is no longer going to be my solvent. It starts to become my solute, at which point I may have a mixture of two volatile species. So think about mixing, say, water and ethanol. Both of them will evaporate to produce a gas phase, and we can get the total vapor pressure of this mixed solvent solute, which is less and less clear of who is who. We're going to be able to figure out the total vapor pressure by knowing how much of each one is evaporating. Now, it's worth noting that this is going to be the momentary vapor pressure. You can relate it to the pure vapor pressure by inserting Raoult's law for both component A and B. And this lets you figure out the total vapor pressure for any mixture of two components. And all you need to do is know the pure vapor pressure of each component and the mole fraction of one component. Because as soon as I know how much A I have, I immediately know how much B. So this gives us only one changing parameter. And so, for example, let's say we're mixing ethanol and methanol. Both of these have very similar IMFs, so they're going to obey this simple Raoult's law expression. So as I start adding in more methanol, the ethanol vapor pressure will decrease as I have less ethanol to evaporate, until eventually it no longer has a vapor pressure of 0 because I have no ethanol and it's entirely methanol. On the converse side, as I add more methanol, we're going to see more and more of the methanol evaporating until once I've got pure methanol, mole fraction of 1, we end up with the total vapor pressure is the same as the methanol vapor pressure. And then simply, if you want to figure out what the total vapor pressure is, just draw a line that links the vapor pressure of the one component, pure component, to the vapor pressure of the second pure component. And again, it is worth noting that this does rely on the fact that they have very similar IMFs. It won't work quite so well if they have different IMFs, which we'll go ahead and look at next time. But one of the real cool parts about this is we can go ahead and look at what happens to the phase composition of the vapor compared to the liquid. So the liquid here is going to be in red. So the mole fraction of methanol in the liquid is going to be the mole fraction of methanol in the liquid. So we have this nice straight line. But a very cool thing ends up happening. If I'm trying to figure out the mole fraction of vapor of methanol in the vapor, I'm going to represent this as Y here to avoid confusion with X. That will be given as the vapor pressure of methanol over the total vapor pressure. Well, we know how to calculate the vapor pressure of methanol. So when we end up drawing this line, what we end up finding is that in general, we're going to end up having the vapor phase will be much richer in the substance with the higher vapor pressure. So this isn't too surprising. Methanol evaporates more easily than ethanol, so I should have more methanol in the vapor phase than methanol. Ethanol should make a lot of sense. Now, one of the coolest implications of this fact is that because vapors tend to be richer in the more volatile component, so the one with the higher vapor pressure, it can be used to try and separate a liquid-liquid mixture. So let's say I have my methanol and ethanol in a solution. I go ahead and I heat it, and we're going to have all of the vapors end up rising until they reach the top, at which point they slowly start to condense, and I get a liquid out on the other end. Well, this liquid will be richer in the substance that's easier to boil. So if I'm mixing methanol and ethanol, it will be much richer in methanol. And so you can heat the mixture just until it starts to begin to boil, and then you'll have some liquid come down on the on your column, and most of the vapor will end up condensing on the other end. And so the vapor will be condensed out as a liquid, which will be richer in the more volatile component. This whole process is called distillation. And if you heat and cool a mixture repeatedly, so let's say I have a mixture of, say, benzene and toluene, I go ahead and I heat it up till it just begins to boil. What we're going to end up with having is At this temperature, the liquid will have the original concentration, but the vapor will be a little bit richer in benzene because benzene's a little more volatile. I then go ahead and condense that benzene, and it will have that vapor, it will have a concentration richer in benzene. And then I do it again, and I'll have a system that's even richer in benzene. And I repeat this over and over again until I'm left with pure benzene and then pure toluene left behind. And this is the major idea with distillation. So what we end up having is the substance with the lower boiling point comes out of the tops. So this is often in distillation called the distillate or the tops. And the higher boiling point liquid, the substance that doesn't want to evaporate, is left behind, called the bottoms. And this is really how we get anything ranging from alcohol to the gasoline in your engine. They're all originally derived from taking a mixture of multiple substances and distilling it. However, so far what we've assumed is that both of these substances have very similar intermolecular forces. They're just as likely to hang out with the other substance in solution as they are with themselves. Benzene and toluene, they don't really see a difference. Methanol, ethanol, not a big difference. However, if we have substances with different intermolecular forces, it has some implications on our everyday life. So next time, we'll be talking about different IMFs and azeotropes. Until then, take care.